Lesson 5, Part 3. Let's start topic about melting glass. So we already know that there are two types of pots are used. Open, crucible type pot and closed covered type pot. And generally closed covered type pot is used. Pot is placed in a circle around a central opening in its bottom. Heated by burning, producer gas and air. A roof of the pots is constructed with reflectory material which also reflect the heat. Also called as batch process. Melting tank furnace. This figure showing tank furnace. This is air and fuel gas. Here will be a molten glass, and from this place you can see fuel gases. The batch is melted in the tank using producer gas and air. It follows regenerative system of heat economy. Air and fuel is passed through the A and B. The burned gases are deflected by the roof and batch gets melted. Hot waste gas escapes through fire bricks C and D. The direction of the fuel gas and air is reversed through C and D, which absorbs the heat of the waste gas and burns. The waste gas now escapes through A and B. Production of flat glass. In 1959, the Pilkington Glass Company in the UK invented this was the floored glass process. This makes it possible to produce perfectly flat, uniform thickness plates of glass in large widths without the need for the expensive grinding and polishing that was always necessary previously. The floored glass process just uses heat and gravity. This figure shows schematic diagrams of the process. The first part of the process is the same as for plate glass. The ribbon of glass is then drawn across the surface of a bath of molten tin. The hot glass floats on the tin and therefore becomes perfectly flat, smooth, and of uniform thickness. As the heat is applied to both faces of the glass, this is fire polishing. It gives perfectly flat and parallel face to the glass sheet. An inert atmosphere protects the tin from oxidation. The selection of tin as the liquid metal on which to float the glass was crucial. It had to be a metal with a sufficiently low melting temperature for it to stay liquid, as the glass cooled to a point where it began to stiffen. The material had to have a significantly higher density than glass, and it was also essential that the glass didn't react chemically with the liquid metal. Tin melts at 232 degrees Celsius and has a density of 7,300 kilograms per cubic meters, nearly 3 times that of glass. It meets all the technical requirements for a substrate material and has proved to be excellent for the purpose. The Pilkington Company protected the process with patents, but an American company quickly developed another version, and the float glass process is now the worldwide standard method for the production of flat glass. So, diagram of the Pilkington float glass process. Here you can see a glass tank of furnace with raw batch. Then you can see a gas in heat zone and fire polishing zone, cooling zone with controlled atmosphere, and this is a liquid metal, and then annealing lathe and cutting section. As has been mentioned already, glass is really a supercooled liquid, and as such it doesn't have a defined melting temperature. Indeed, it doesn't melt in the conventional sense of the term. Rather, it softens as it's heated, its viscosity decreasing with increasing temperature until it becomes truly liquid. The next figure illustrates how viscosity reduces as glass is heated. These four curves are for pure silica. Pyrex, boron silicate glass, container glass and lead glass. The trend shown is quite clear. As the temperature is increased, the viscosity of the four glass type reduces. In everyday parlance, the glasses become more runny or more liquid. The strain point is the temperature at which any internal stresses are reduced significantly in a matter of hours. The annealing point is the temperature at which any internal stresses are reduced to a commercially acceptable level in a matter of minutes. Below the strain and annealing point line lies the working range, bounded by the two horizontal dashed lines. In some texts, upper and lower line of this range are designed the softening point and the working point. However, from our point of view, the working range is the important temperature range for shaping glass product. Melting chemical reactions. Raw material melts at relatively low temperature and assists in melting of rest of the charge. During the melting process, following reactions occur. Calcium carbonate plus silicon oxide will be a silic oxide plus CO2. Sodium carbonate plus silica oxide will be a natrium to silica oxide 3 plus CO2. The molten mass is heated till it's free from air bubbles. For colored gases, desired pigment is added. The molten mass is then cooled at about 800 degrees Celsius at a later point of time. Forming and shaping, annealing and finishing. In order to shape glass into the various products with which we are familiar, the glass must be heated to an elevated temperature. Molten glass is converted to desired shape by blowing or molding or pressing between rollers, forming and shaping. Articles are then cooled gradually at room temperature. Annealing. The longer the annealing period, better the quality of glass. After annealing, the articles are subjected to cleaning, polishing, cutting, sandblasting, etc. and this process called finishing. So, forming and shaping, annealing and finishing. It's important to recognize that when heated, glass doesn't melt in the conventional sense. There is no fixed temperature at which glass passes from solid to liquid. Rather, the glass progressively softens and the temperature is raised. This is why glass is sometimes called a supercooled liquid. We can distinguish a number of glass shaping processes. Production of flat glass for glazing. Production of glass fibers short and long. Production of glass wool. And production of bottle and containers. Of these, the first three are of interest to the construction industry. Production of glass wool insulation. Glass wool can be made using a centrifugal spinner. Fibrous wool-like material composed of mixed fine filaments of glass. Alkali-free. Glass filaments are obtained by forcing molten glass through small holes with which measures about 0.0005 to 0.0007 millimeter in diameter. Properties: very good fireproof and heat-proof, very low electrical conductivity and thermal conductivity, resistance to water and most chemicals. Uses: heat insulation purpose, electrical and sound insulation, filtration of corrosive liquids like acids, manufacturing fiber glass by blending with plastic resins. And production. Like already I have told, glass wool can be made using a centrifugal spinner. Jets of air can be directed downwards onto the emerging filaments so that they remain continuous, and then the fibrous material can be sprayed with an organic binder so that the familiar glass wool blank material is produced. A schematic of the process is given in this figure, a rotary process for glass wool production. Glass wool works as insulation because of the pockets of air cut in the mass of fibers. Air is a poor conductor of heat, and so the wool acts as a glass-air composite and provides good thermal insulation. It's easy and convenient to apply inside building, roof structure, etc. So this is a glass melter and this is a 4 hairs. Through stream of melted glass, and it's to centrifugal spinner, air jet on the left and on the right, and binder spray in Felton chamber, and then anchored fiber blanket and carrying oven. On collecting and conveying chain, air suction through chain. The manufacture of bottles and containers from glass is a large industrial sector, but it's not relevant to construction, and so it will not be considered here. Type of glasses: soda lime or soft glass, potash lime or hard glass, lead glass or flint glass, borosilicate glass, aluminosilicate glass, optical or Crookes glass, glass wool, quartz glass, opal glass. Soda lime or soft glass. Raw material: silica, calcium carbonate, soda, ash. Composition: sodium oxide, calcium oxide, silica oxide. Properties: low cost, resistant to water, attacked by acids, melts easily, molded easily to any shape, poor thermal and chemical resistance. Uses: window glasses, electric bulbs, bottles, jars, tableware, etc. Potash lime, hard glass. Potash lime, this is a hard glass. Raw materials: silica, calcium carbonate, kalium carbonate. Composition: kalium oxide, calcium oxide, silica oxide too. Properties: high melting point, not attacked by acids, alkali and other solvents. More expensive than soda lime glass. Uses: combustion tubes, chemical apparatus. Lead glass or flint glass. Raw materials: silica, lead oxide, potassium oxide. Composition: plumboum oxide, kalium oxide, silica oxide. Properties: bright, glossy and possesses high weight. Expensive to manufacture than ordinary lime soda glass. The lowest softening temperature than soda lime glass. Higher reflective index and excellent electrical properties. Uses: high quality tableware, neon sign tubings, optical lenses. High dense glasses are used for windows to protect from X-rays and gamma rays.